that we were.
Yeah, oopsie.
No worries. Okay. Yeah, so I was saying, right, with multi-version databases, one of the questions is how do we choose and assign versions? They should be consistent, meaning that the version of a previous transaction should be smaller than the version of a transaction happening in the future. And efficient means that it should not impact the transaction. So how do we do this? Well, one approach is to use timestamps, right? To use the timestamps as versions, but ordering these timestamps is not really trivial. There are several approaches. One of them is using a physical clock. Has literally zero cost because you can just read from the machine, except it's not actually consistent because of unsynchronized clocks. Then there's the global logical clock, GTS, which is easy to ensure consistency, but it doesn't actually is non-trivial in terms of cost because we essentially have an oracle that keeps track of the clocks, and we essentially have to make network requests every time we want to request a new clock. And with enough scale, that central oracle becomes a bottleneck. So this is what GTS server looks like. Each transaction, for every transaction, you need to basically read from the timestamp server, which is the global source of truth. And as we can see here, just the network is where we incur most of our costs. The other alternative is VTS, which is a global vectorized clock in which each worker contains its own logical clock. And this reduces the request to the global server, but it does not eliminate it because the global clock, we still need a global central oracle that keeps track of all of the worker clocks in order to actually provide consistency. So we have a non-scalable metadata. We have one clock per worker, and with sufficient scale, this also becomes well, it becomes a bottleneck, the oracle, but also we're using more and more resources as more and more workers join. This is an example of VTS. So each transaction or worker has its own clock, but the global, the timestamp server has a version of all the clocks. The paper actually did a really good job explaining this too with separate diagrams and several examples that you can follow on your own. So what they propose in the paper is a decentralized scalar timestamp. It's a scalable scalar timestamp mechanism to enable MVCC, and provides a snapshot reads for read-only transactions, and it's consistent and efficient scalar hybrid physical clock. Reader uses the physical clock to read snapshots. It bypasses the concurrency controls, and the ST is consistent by piggybacking with read-write transactions concurrency control. I think the main idea here is that it basically uses, instead of using a separate server, right, a mechanism for requesting the timestamp, it basically modifies existing concurrency controls like two-phase locking, and by using that, it's how it's able to derive the timestamps in a consistent fashion. And we'll see examples of this further on. In order to better explain how it works, right, let's first define certain properties of a conflicting transaction and what should happen with correct concurrency controls. So let's take an example where transaction A commits before transaction B, and both of them are accessing tuple O. We define three properties of what should actually happen. In the write property, transaction B should overwrite transaction A or generate a new version. For write-read, transaction B should be able to read transaction A, or whatever was written in transaction A. And then read-write, transaction A should not read the write of transaction B because transaction B happened after transaction A. So let's look at how they integrate DST in existing, in a two-phase locking approach. You usually start with writing A, you do a lock on A, the server grants you the lock, then you do other things, and then you essentially commit, in which the server writes A and then unlocks A, and that's how you're able to do a write. Any other concurrent transaction that happens trying to write A will have to wait until we release the lock. The way it integrates this with DST is as follows. So when it has a start in which it just basically gets the timestamp of the clock. Then it sets a lock, and it retrieves the version of A. Then the transaction calculates a new timestamp, which is the maximum of either the one that it currently has or the version that it retrieved from the server, and then +1. And then when it finally writes it, we essentially write the new value of A, set the new version to be the timestamp, the new timestamp that we calculated, and then we unlock A. For write-read, well, the presentation skipped the diagrams for this, but and also skipped in general the followings, but let's go through them just to make sense of them. Transaction A installs the new value A with a commit timestamp TSA into tuple O, and transaction B then reads the value A of tuple O with the timestamp OTS, and then installs a larger commit timestamp B. So an example of this is if we look at, and this is from the paper, if we look transaction 1 commits before transaction 3, and as we see here is the little squares. So the black dots are basically the local timestamps of the worker. The little squares are the versions for that specific tuple. And so we see that transaction 1 commits before transaction 3, and we see that therefore the transaction 3 timestamp should be larger than the one of transaction 1. So using DST, transaction 1 installs its value into the commit timestamp TS. So the timestamp of 1 is 4, which is derived here. And then after that, transaction 3 reads the timestamps of tuple A, which is 4 because it was committed by worker 1, and then derives a larger timestamp, which is 5. For the read-write property, we have transaction A install a commit timestamp TSA into tuple O, since it has read the value of O. And then transaction B reads the timestamp of tuple O and installs the new value V with a larger timestamp B into tuple O. So similarly here, this is the same diagram. Transaction 1 again commits before transaction 3. Transaction 1 reads tuple B before transaction 3 writes it over here. And then using DST, transaction 1 reads an old value. So in this case, B has a value of 5. And after it installs a new timestamp into tuple B, which is timestamp 4. And then after that, the transaction 3 will derive a larger timestamp and use it to install it into tuple B. So the larger timestamp here, we see 5 is installed here once we overwrite it from 5 to 2. So then they go on to mention that in its original, well, not original design, but in its current form, the read-only transactions can directly pick any timestamp to read a consistent snapshot by comparing its read timestamps with timestamp of tuples. But since read-only transactions do not follow any concurrency controls, it is possible for a read-only transaction to read part of a concurrent read-write transaction. So I modified the original diagram first to show the problem here. And if we look at transaction 4, And transaction 3, they're essentially concurrent transactions because they have not committed. Both of them start, none of them have committed. And in this scenario where transaction 4 is a read-only transaction, we're reading C, A, and B. Transaction C is unlocked. No other concurrent transaction is actually touching it, so we can read the value immediately. However, for A and B, transaction 3 is actually modifying them. So it is possible in the current form of DST that we read an old value of A, but a new value of B, if this update happens in between these two reads. So we could end up reading an old version of tuple A where the value is 5, which is what it was updated on transaction 1. But instead of reading 5 as well, which was the original version of B, we actually read the new version, which is 2, which was done by transaction 3. And they describe a simple way of accounting for this so that we don't have this happen. Oh, and also one of the problem with this, right, is that we essentially don't wait at all. We notice that if we notice in here, worker 3 has a larger timestamp 7, and it essentially just doesn't wait for anything to happen because it's reading essentially old values. So we can achieve serializability with read-only transactions, and this is done by making sure that read-only transactions claim all of its operations before reading the tuples. So it first installs its read timestamps into a tuple and waits until the conflicting read-write transactions commit if the timestamp of the tuple is not larger than the read timestamp. So the updated version of this is that we're seeing that because worker 3 has a larger timestamp, which is timestamp 7, we read C because it's not actually locked by anything. But when we look at A, we notice that the value that is at A is smaller than our current timestamp. So we wait for, well, it would also be locked. So we basically wait until the concurrent read-write transaction finishes. And then once it's finished, we're able to read A and B with its updated values, 3 for A and 2 for B. And then we commit, we insert the new timestamp into both A and B. Yeah, and essentially the last thing mentioned here is that DST uses hybrid timestamp, and this way it's able to achieve bounded staleness. So it achieves a combination, it adopts a combination of a physical clock and a logical clock as a hybrid timestamp. It uses a loosely synchronized clock as the physical part and monotonically increasing counter as the logical part. The logical part is used to avoid possible overflow of the physical part, since the timestamp will be incremented when calculating the maximum timestamp. And then the physical part is used to ensure that the read-only transactions can read from a fresh, so relatively fresh snapshot. The paper then goes on to prove theorems of bounded staleness, and it also talks about how this can be applied to multiple concurrency controls, not just two-phase locking. And it also talks about the other protocols such as OCC and Rococo. And well, I mean, I didn't cover this in the presentation, but it talks about the results on various mechanisms and also the improved performance against JTS and BTS. One of the interesting parts about the performance was, well, that I found interesting was as it increased the number of workers, you saw the performance decline for BTS because you're carrying more and more metadata with each worker carrying its own clock. But leaving that for the readers to look at on their own time. And that's it.